In the previous video, we looked at the convergence of this series, and we used the ratio test. So with the ratio test, we always need to compute this value here, and performing the ratio test led us to this, led us to this, led us to this. So from here, if you look at this, as n heads towards infinity, this thing is going to head towards 1. So we will have convergence if the modulus of this is strictly less than 1. And we've concluded that if x is anywhere in between here, then we know the series is going to converge. Now in this video, we need to look at the endpoints. In this video, we are going to look at this point here, this endpoint here, when x equals 1. So when x equals 1, so to consider the endpoint when x equals 1, let's look at the original series. This would then become this. So we need to evaluate this series. Now when x equals 1, we will put it into here. So this will be 1, put it into here, 1, put it into here, 1, and so on. So everything here, when you put 1 into here, 1 to the power of n, as n moves to infinity, this is going to be 1. So we can pretty much ignore this. We can ignore this x, we can ignore this, we can ignore this, and so on, because we are looking at the end point at when x equals 1. So with the ratio test, we always need to compute this value here. So at x equals 1, put 1 into here. This is going to be 1, so we can ignore this. Put 1 into here. Well, we can ignore this. So it really boils down to this whole thing here, boils down to this. So now tidy this up. So rewrite this as one block multiplying another block. These two will cancel out, giving you this, and then tidy up, and it will then lead you to here. So this value here, when it comes to the ratio test, we always need to compute this value here. Well, this value here is equal to this. Now, hang on. So now but don't forget, as n tends to infinity, yes, this whole thing here heads towards 1. It heads towards 1. But because we don't have this x anymore, because x equals 1, we don't have this modulus of x anymore. As n heads towards infinity, even though this whole thing here heads towards 1, don't forget it could be on the underside of 1, so it could be 0.999999. So in which case here, this value here is equal to this. So let me take one step back. This whole thing here, the limit is actually heading towards 1, but it could be the underside of 1. So this value here, for example, if the numerator is smaller than the denominator, then you're going to get something like 0.99999. It is heading towards the limit, is heading towards 1, but it could be the underside of 1. In which case we will have convergence because this is less than 1. Or you can have a scenario where even though the limit of this is heading towards 1, it could be the upper side of 1. So it could be, if this is slightly bigger than the denominator, then you're going to have 0.0000023, whatever, 4, 7, whatever. But the point is that this thing here is above 1. So we're going to have divergence. So even though the limit is heading towards 1, it could be the underside of 1, or it could be the upper side of 1. So it depends. It could still converge. It could still diverge. So now let's look at a case where let's say let's try and look at this bit and try and understand this bit. If k is 7, not to scale, let's just say 7 is here. So what that means is k equals 7. You put 7 into here. You put 7 into here, and you put 7 into here. Let's just say k equals 7. So now 7, take away n. Remember, n is moving towards infinity. So let's just say currently it is increasing. Currently n is at 100. Remember, n goes all the way to infinity. Let's just say currently n is 100. So here you've got 7. Here you've got 7. Here you've got 7. Take away 100. So going back all the way here, not to scale. So this is now at negative 93. Now take the modulus of this thing here, which will be positive 93. And then now you've got 101 at the bottom, 101 at the bottom. So now you can see that this is on the underside of 1. So I don't know what this is, probably, I don't know. It's going to be less than 1. So here you will have convergence. So at x equals 1, at x equals 1, at x equals 1, it depends on k. If k is, you can see that well, when k is 7, if you take away 100, that will then give you this distance here. So when you take the modulus of this distance here is 93, and then the denominator here will be 101. So the point is that this distance, which is the numerator, the numerator will always be smaller than the denominator. So it's going to be less. So in which case you're going to have convergence. Let's just say k is let's just say k is 0.8. So now let's say n. It could be 1,000, it could be 1 million. Let's just say it's 100. So now when k is 0.8, you take away 100. So this is going to be 99.2. So negative 99.2. Now you take the modulus of this, it will be 99.2. And then when you look at the denominator, it will be 100 plus 1, it will be 101. So this value here is still less than 1. So it's going to converge. Now let's say k is less than 0. So k is negative 0.0, let's say 3. Now when n gets to 100, so remember n's moving all the way to infinity. When n gets to 100, so you start here, take away 100, so you're going to end up with negative 100 at 0.3 here. Take the modulus of this, that will then give you 100.3, and then if you look at the denominator will be 101. It's still less than 1. The point here is that if your k is less than negative 1, let's say negative let's just say negative 2, k equals negative 2, then when you take away 100, that will give you negative 102. Take the modulus of that, that would be this, and then the denominator will be this. Now this thing is going to be bigger than 1, so it's going to diverge. The point here is that when x equals 1, we will have convergence if k is greater than negative 1. Okay.